Assalamualaikum warahmatullahi wabarakatuh. Om Swastiastu, Namo Buddhaya, Salam Kebajikan. Hello, my name is Kiflan, and today I am going to discuss about wave and their behaviors. First of all, this video is created for fulfilling my physics task, chapter 8, grade 11th, physics for high school. Wave. What is wave? According to Merriam-Webster dictionary, wave is a moving ridge or swell on the surface of a liquid, as of the sea. Recall from the grade 10th chapter of oscillation, oscillations that means the back and forth movement between 2 points that involve force and energy. More precisely, a wave is a disturbance that propagates or moves from the place it was created to its destination. Now that oscillation can create waves such as sound, light, or on water. But today we will not discuss wave thoroughly. Just one specific subchapter, wave behaviors. Wave behaviors are split into 7 different parts. They are reflection, refraction, diffraction, interference, constructive interference, destructive interference, and Doppler Effect. Firstly, reflection. Reflection is the change in direction of a wave when it bounces off a barrier, such as a fixed end. When the wave hits the fixed end, it changes direction and inverted. If a wave hits with a crest, it will return as a throw, and vice versa. If it hits with throw, it would return as a crest. When a wave propagates through a medium, it reflects when it encounters the boundary of the medium. The wave before hitting the boundary is known as the incident wave. The wave after encountering the boundary is known as the reflected wave. As you can see here on the picture, the angle of reflection R is 60 degrees. Incidence at other angle shows that the angle of incidence and angle of reflection are always equal. And another picture here, you can see one end of the string is fixed so that it cannot move. A wave propagating on the string, encountering this fixed boundary condition, is reflected 180 degrees or p radian out of phase with respect to the incident wave. The below one, you can see that one end of a string is tied to a solid ring of negligible mass on a frictionless lap hole. Where the ring is free to move, a wave propagating on the string, encountering this free boundary condition, is reflected in a phase of 0 degree or 0 radian with respect to the wave. Next, we have refraction. Refraction is a change which in the direction of travel of the waves, which occurs when their speed and hence wavelength changes, or it can be defined as the changing of a light ray's direction, loosely called bending. When it passes through variations in matter, refraction is responsible for a tremendous range of optical phenomena, from the action of lenses to voice transmission through optical fibers. As you can look, first example of refraction with waves in shallow water have a shorter wavelength, or picture 2, where waves are refracted at the boundary between deep and shallow region, and picture 3 that explained the direction of travel of the wave is bent toward the normal in the shallower region. And the last picture where refraction come into place in technology or fiber optics that change the light ray's direction or bending to its destination. After that, we have diffraction. Diffraction is the spreading of waves at the edges of obstacles. What happens when a wave passes through an opening, such as light shining through an open door into a dark room? For light, we expect to see a sharp shadow of the doorway on the floor of the room. and we expect no light to bend around the corners into the other part of the room. When sound passes through a door, we expect to hear it everywhere in the room and thus expect that sound spreads out when passing through such an opening. What is the difference between the behavior of sound waves and light waves in this case? The answer is that light has very short wavelengths and acts like a ray, like a gamma ray, for example. Sound has a wavelength on the order of the size of the door and bends around the corners. Another examples are in water. On the first picture, you see a spreading that occurs after waves passing a narrow gap, and the second picture after they pass a wide gap, and the breathing looked less obvious. We use these behaviors when designing harbors, such as in this picture. Now, I want you to look at the picture. When two sets of continuous circular waves cross in a ripple tank, a pattern, like in the picture, at points where a crest from one source, S1, the red thingy, arrives at the same time as a crest from the other source, S2, the yellow thing. A bigger crest is formed, and the waves are said to be in phase. At points where a crest and a throw arrive together, they cancel out each other, if their amplitudes are equal, of course. The waves are exactly out of phase because they have traveled different distances from S1, the red thingy, and S2, the yellow thingy, and the water is undisturbed. In the picture, the blurred lines radiating from between S1 and S2 join such points. It is called interference or superposition. That means the combination of waves to give a larger or a smaller wave, or disturbances of waves are superimposed when they come together. Then, this picture shows two identical waves that arrive at the same point exactly in phase. The crests of the two waves are precisely aligned, as are the throws. This superposition produces pure constructive interference. Because the disturbances add pure constructive interference produces a wave that has twice the amplitude of the individual waves, but has the same wavelength. While in this picture, the next picture shows two identical waves that arrive exactly out of phase. That is, precisely aligned crest to throw, producing pure destructive interference. Because the disturbances are in the opposite direction of this superposition, the resulting amplitude is zero. For pure destructive interference, the waves completely cancel. You know what? That this is the noise-cancelling headphones. The first generation of noise-cancelling headphones use this technique actually. Fun fact! Last one, we have the Doppler effect. The Doppler effect is an alteration in the observed frequency of a sound due to a motion of either the source or the observer. Although less familiar, this effect is easily noticed for a stationary source and a moving observer. For example, if you ride a train past a stationary warning bell, you will hear the bell's frequency shift from high to low as you pass by. The actual change in frequency due to a relative motion of source and the observer is called a Doppler shift. This picture explains that the sounds emitted by a source moving to the right spread out from the points at which they were emitted. The wavelength is reduced and consequentially the frequency is increased in the direction of motion, so that the observer on the right hears a higher pitch sound, and the opposite is true for the observer on the left, where the wavelength is increased and the frequency is reduced. And then this one explains that the same effect is produced when the observer moves relative to the source. Motion toward the source increases frequency as the observer on the right passes through, more wave crest than she would if stationary. Motion away from the source decreases frequency as the observer on the left passes through fewer wave crests than he would if stationary. Alright, maybe that is all. I am very sorry if this video lack touch and details and everything. It was made just in a few hours and I am so sorry for everything. Thank you for watching. Wassalamualaikum warahmatullahi wabarakatuh.